Hello, AP Calculus AB, and welcome to Day 84, Interpreting Tabular Data. As a reminder, tabular data is data presented in a table. So we have 6 problems to go through today, and each problem is going to have a table like this. Oftentimes, the table is going to present data in terms of giving you an output that's a rate, but not always. You 100% need a graphing calculator for today. We're going to practice pretty much every feature that you're required to use on your graphing calculator as we go through these problems. I am also not going to do every part of every problem. I do have my solutions posted. And so you can check your work there, but I want to make sure I'm not doing, the same style problem over and over again. Your worksheet might look a little different than mine. For this presentation, I added in some spaces for me to do the problems, but on your worksheet, I condensed it so I would print out fewer pieces of paper. So that's why I have all these boxes, but problem 1 and problem 2 that you'll see here are the same problem 1 and problem 2 that you have, just on 2 pages instead of 1. So let's get to it. Let y of t represent the population of the town of Sugar Mill over a 10-year period, where y is a differentiable function of t. The table below shows the population recorded every 2 years. So if we wanted to read this table right, in the second year, there's a population of 2,912 people in the town of Sugar Mill. We are going to use the data from the table to find an approximation for y prime of 7 and then explain what y prime of 7 means in terms of the population of Sugar Mill. So let's begin. First thing you might notice looking at the table is that there is no 7. We've discussed this before, though. When you are asked to find the derivative of a value in a table and you don't have that value there, then you need to take the two closest t values, in this case, to 7, one above, one below, and you need to find the slope between them. Now, it turns out that 7 is exactly in between 6 and 8, but even if this was 9 right here, you would still take those two, even if 7's not exactly in between, because the idea isn't necessarily that the slope between these two values is going to be exactly 7. It's just that the mean value theorem is going to guarantee, since y is differentiable, is going to guarantee some point in between 6 and 8 that will be equal to the slope of the endpoints, and maybe it's 7. Again, I've expressed my displeasure with this style of problem, but it's common enough that it's worth discussing. So how does this work? Well, we're going to say that y prime of 7 is approximated by, and then we're going to find y of 8 minus y of 6 divided by 8 minus 6. And continuing through, we have 4330 minus 3815 divided by 2. And then this is probably where your calculator is going to come in, right? 4330 minus 3815. So we have, let's make this into a fraction, I think. And we know we're dividing by 2. And I've already forgotten both numbers. 4330 3815. 4330 minus 3815. And then we can hit enter, but that's going to keep it as a fraction. And since we're dealing with people, we should probably approximate that as a decimal, 257.5. 257.5. Well, that's exciting. That might probably gain us 1 point on a free response, but then we're asked to explain the meaning of y prime of 7 in terms of the population of Sugar Mill. The easiest way to do that is to think about the units. And how do we know the units? Well, let's go back to the table and think about where the units belong. People goes with all of these population numbers, so we have people up above. And then we have years, which are these t values which went down below. So we can see that we created 257.5 people per year. And it might even help you to think of this as a fraction. So what is this saying? This is saying remember, derivatives always talk about what happens at a specific value. At t equals 7 years, what's happening? Well, we found the derivative of people, or the derivative of the population, and a derivative always measures a rate of change. So we can say the population is changing at 257.5 people per year. Now, you could also substitute the word changing with increasing because we got a positive answer, but I think changing is the safest way to put that. All right, let's continue through. Use the data from the table to approximate the average population of Sugar Mill from 0 to 10 by using a left Riemann sum with 5 equal subintervals. Now, I'm always a big fan of first showing the integral of what we're trying to do. So I like to do the integral of what? Well, the integral of, in the table, we have y of t dt, right? And we're saying that this is going to be approximated by, well, a left Riemann sum. So they also told us that there are going to be 5 equal subintervals. Let's make sure there are 5 subintervals. First, second, third, fourth. There are 5 subintervals, and because it's a left Riemann sum, we're going to exclude the last endpoint. We should also notice that each subinterval has a length, picture the x-axis, of 2, which means I can factor out that 2 from everything, which is very exciting. We'll keep that same color. Then we need to just sum up the heights of the 5 different rectangles. So 2500 plus 2112, and so on and so forth. Okay, all the way up to 4330. Don't do that on the AP exam. Write all the numbers. Awesome. All right, so then we are going to get an answer. Now, when you do all of this on your calculator, and I went ahead and just kind of paused the video just to get everything done, I got 16917. 16917. Awesome. And then you can multiply that by 2, and you'll get your final answer. Or is it our final answer? Let's take a look at these units really quickly. They wanted us to approximate the average population. Now, what are the units of average population? Well, that's just going to be people. On average, there were this many people in the town. But if I look at my units over here, y of t is in people, and we're multiplying that times dt, where in an integration problem, dt is an infinitely small interval on the x-axis. In this case, it's actually a tangible interval of 2, but our t values are in terms of years. And so if I multiply these two together, I'm going to get units of people years. I'm not even sure what units of people years are, but I'm quite certain that those are not the units that I want. In fact, we missed a small part of this, and I did actually do this on purpose. They asked us to find the average population. And if I want to find the average value of the population, then we do need to incorporate the average value theorem, right? We went from 0 to 10, and I need to divide by 1 over 10 minus 0. And the reason that works is because 10 and 0 are time values. So I need to have this 1/10 out front because 10 minus 0 is in terms of years. And so this will give us people years. We'll be dividing by years. And if we think about what happens with our units, these cancel. And so we can end up with 2 over 10 is 1/5, I think. 1/5 of 16917. And I have that answer somewhere. I'm just going to quickly check down to my solutions. I know it's 3,000 something. 3,383.4. 3,383.4. 383.4 people, right? Looking at that final unit. We also could have known that if you just multiplied these two together, you probably did not get the average population, right? Because that's going to be 33,000 something. And there's never been a year where there were 33,000 people in the town. Really just eyeballing it, doesn't it seem like these two are in the middle, and so probably our average population should be somewhere in the 3,000 range, which is what I found here. Yeah, so just be careful with those units. I think they'll really help you come up with your right answer. Let's move on to part C. A model for the population of another town, Pine Grove, over the same 10-year period is given by the function p of t equals, okay, so now we have an equation. Use the model to find the value of p prime of 7. Now, I am well aware that you can say, ooh, cool, P of t is this, and it's not a bad thing to practice your derivative rules. And you're like, P prime of t, we do d dt of each side is 2 times 2t plus 50 to the first times the derivative of the inside, which is 2. And so cleaning this up, we get 4 times 2t plus 50. That's great. Then, from here, you would find p prime of 7. But because all of these are calculator active, we really need to get to practicing our calculator active skills, because there are going to be some problems where you are required to use your calculator to do this, or at least expected to. And so what I'm going to do is I'm just going to go straight to finding p prime of 7 using this equation, 2t plus 50 squared. Okay? We're going to do it with our calculator. So menu, calculus, derivative at a point, and we can use x, that's fine. We're evaluating this function at 7, and it was 2x in this case, plus 50, and squared. Enter. Great. 256. 256. This is all that would be required on this entire problem. None of this. This is calculator active. Now, you could check it. You could substitute 7 in here. 14 plus 50 is 64 times 4 is 256. So that is right. But again, if it is calculator active and you have the chance to use your calculator, please do so. All right, part D. Use the model given in part C, so this guy up here, to find this value. Okay, well, that means we're going to do 1/10 of the integral from 0 to 10 of p of t dt. And I'm going to do all of this on my calculator again. So we have our fraction 1/10. And this is being multiplied by menu calculus, our integral, from 0 to 10 of, and then that same equation. So 2x plus 50 squared, and then dx. Great. And we got 10,900 over 3. Let's go ahead and make that into a decimal. 3633.33. 3633.33. Be careful. I'm suspect that it ends in 0.33. Let's look at the full value of that decimal. Oh, there's an extra 3 down there. So we definitely want to put the extra one there. Explain the meaning. What does this integral tell us? Well, this is our average value theorem. It's going to tell us the average value of whatever p of t is. So what is p of t? Well, p of t is measured in people. So this is going to be the average number of people. All right, so as we look through, how do we explain that? We would say the average number of people in Pine Grove from t equals 0 to t equals 10 is 3633.333 people. And there we go. Okie dokie, let's jump down to problem 2. Now, I did promise you I wouldn't go through all of these. I especially hate repeating myself when you can do it just fine. So the two problems I'd like you to try on here are problems A and C. I think both of those should be just fine. This is, again, calculator active. You should strive to use your calculator for part C. Part A is very, very similar. You might want to try 15 and 20. You'll notice that 18 isn't exactly in between there, but as long as it's somewhere in between, that's just fine. But what are we going to do? Well, first we're going to understand this problem, and then we're going to talk part B. So, let y of t represent the temperature of a pie that's been removed from a 450-degree oven and left to cool in a room with a temperature of 72 degrees Fahrenheit. Y is differentiable, temperature recorded every 5 minutes. Well, this is actually pretty relevant because I just made dinner. My wife and I did pizza from scratch, so we'll call it a pizza pie, and I baked it in a 450-degree oven, so how exciting. So you remove the pizza, and our room temperature is a little bit cooler. I'm a little stingy with the thermostat in the house, but that's okay. So you remove the pizza, and then, of course, as time progresses, what should happen to the temperature? Oh yeah, the temperature, of course, goes down. All right, so part B. Use the data from the table to find the value of the following integral. Integral from 10 to 25 of y prime of t dt. Now, what I've seen people do before, which is a clever idea, but not what they want here, is they say, oh, if I'm going to do this, I'm starting at 10, I'm ending at 25, and I see like 1, 2, 3 subintervals. So let's maybe do a left or a right Riemann sum. Well, two things are wrong with that. First, this problem is asking about y prime of t, and an integral always measures the area underneath this graph, the graph that's inside the integral, the integrand. So in order to do an approximation, you would have to have values of y prime. Second, nowhere in part B does it say use the data to find the approximate value of the following integral. It just says find the value, which means there is an exact answer and there is no reason to be doing an approximation. So remember, there are two ways to evaluate a definite integral. Option one is you have the graph and you find the exact area underneath the graph, but I don't have the graph of this. So option two is to use the fundamental theorem of calculus. So we always write out what we're trying to evaluate. So this is the integral from 10 to 25 y prime of t dt, and we're going to use the fundamental theorem. The fundamental theorem says first take the antiderivative of y prime, which is very doable. That's just y of t. We still need to evaluate this from 10 to 25, or 12 in Mr. Grantland. Continuing to evaluate this integral, we go from 10 to 25, just rewriting where we started, and we use the fundamental theorem. Y of 25 minus y of 10. And continuing to work this out, we have these values. They give them to us in the table. Y of 25 is after 25 minutes, our pizza is 226 degrees. It's a very slow cooling pizza, I think. And after 10 minutes, the pizza was 338 degrees. And so if we continue with this out, I think we end up getting, what, negative 112, it looks like? 2 and 6 is 8, 1 and 3, 1 and 3. Yeah. Okay. So negative 112 degrees. It says indicate units of measure. So degrees what? Oh, degrees Fahrenheit. Yeah, I guess if this was degrees Celsius, we might have not been quite as, might have maybe had some smaller values to deal with. Cool, but then it says explain the meaning of the integral in terms of the temperature of the pie. Explanation time. Here we go. Not at t equals 25, not at t equals 10. An integral sums up what happens over a time interval. So, from t equals 10 to t equals 25, the pizza's what? What do these y values measure? These y values measure temperature, don't they? So the pizza's temperature, and then the safe way to say this is the pizza's temperature, I'm not sure why I wrote is, changed by negative 112 degrees Fahrenheit. All right, now someone will say, well, wait, why would it change by negative 112? That seems really weird. Shouldn't we maybe explain which direction it moved? Sure, that's totally fine. So if you didn't want to say that and you wanted to say something else, then maybe our something else could be decreased by, but then be careful, we need to say it decreased by positive 112 degrees Fahrenheit. If you say decreased by a negative, now you're increasing, and the temperature certainly did not increase from 10 minutes to 25 minutes. So you can say decreased, but you need to leave off that negative. Changed is a really easy word to use, though, because then you can just put your answer every time, and the negative will take care of itself. Nifty. Last but not least, use the model given in Part C. So Part C says, cool, you looked at a table, now you're looking at an equation to find the time at which the temperature of the pizza pie, and I know it's pie, but I'm going pizza because that's what I have for dinner, is 300 degrees Fahrenheit. All right, well, this is in degrees Fahrenheit, and they're asking when is the pizza itself 300 degrees Fahrenheit. In fact, Part D uses no calculus at all because we're not changing our units. They gave us an equation in degrees. They want to know when is the equation 300 degrees. That there's a time as an input and W is the output. So I think in order to solve this, we would take 300 and set that equal to 72 plus 380 e to the negative 0.035 t. And then solve. Now, one way to solve this is, of course, and you'll find an exact answer, to isolate t. You'll need a natural log in there at some point. There's nothing wrong with it. But because this is calculator active, as soon as I saw that it was calculator active, I typed in the equation w of t equals 72 plus 380e to the negative 0.035. I used x, but t in this case, into my graphing part of my calculator because I assumed that I would probably want that to use at some point. So if I go to my graphing part of my calculator, you'll see that same equation. Make sure you use x instead of t though, because this is a function of x. You better use x all the way through here. Now when I hit enter though, we see nothing. I'm like, drat, why are we seeing nothing? Well, it is, I think, because, look at this. It says we're going to do 72 plus 380 times something. So we're like, whoa, okay, well, what am I going to do here? Well, if we're looking for where the temperature of the pie is 300 degrees, let's take a look here. Clearly, 300 degrees is going to occur between 10 and 15. So if I wanted to set my axes to see everything, right, I'm going to go through and I'm going to say, okay, well, let's actually see the whole pattern here. Let's go from 0 to 30, all right? And we know the y values, 450 to 200. So this is actually helping me set my axes, right? So we're going to go to Menu, and then Window Zoom, Window Settings. We want to go from t equals 0 to t equals 12. And we said we're going to go from, don't go 450 to 200 because we have to put the smaller one first. We'll go 200 to 450 and hit enter. Look at that. There's my equation. How exciting. Now, there's my equation, but I said that we were going to go through and solve this. But we need to remember that a second way to solve an equation, and you are required to use this method at some point throughout the AP exam, is you graph each side of the equation. Essentially, we're splitting this into a system of equations. And you don't have to write this, but what we're doing is we're going to graph y equals 300, and then we're going to graph y equals this guy up here. And don't forget that the solution to a system of equations is where those two equations overlap or intersect with each other. So I think I just need to graph a second line of y equals 300. Oh, I can't even see it. That makes me curious if I messed something up here. Let's take a look. 72 plus 380e to the negative 0 point whatever. Temperature is 300. Model of the temperature, 72, 380, negative 0.035 T. I don't see anything on there. That's a bummer because that's 12 and, oh, it was supposed to go to 30. Well, that's awkward. Okay, let's change this. No harm done. You're probably looking at this like, why did he have us go to 12? Well, for some reason I had 12 stuck in my head because I'm a crazy person, and let's go to 30. There we go. Hey, look, now they intersect each other. I'm so proud of us. Okay, so Menu, Analyze Graph. Let's find their intersection, which is 4. Okay, lower bound, we go to the left of their intersection point, drag to the upper bound. We get 14.6, but I don't trust that. I'm going to hit the plus button a few times, see a few more decimals. There we go, 14.595. All right, so use the model given. You do need to write this step because when solving any equation, you always need to show the setup and the answer. So here is my setup, and then my answer is that t is approximately the number I already forgot, 14.595. 14.595. There we go. That's it. That's all there was to it. Now, would you have this problem on the AP exam? No, because no part of it required calculus. Now, if this was W prime, and this is where the AP exam can get a little shifty, and so if they said W prime, and they're like, W prime is measured in degrees Fahrenheit per minute, and they're like, find the time at which the temperature, or at which the degrees Fahrenheit per minute is 300, you'd set up the same thing, you'd solve the same thing, but now we've used calculus because this equation was a calculus equation with W prime, so it's a very fine line. Will you have to do this on the AP exam? Guaranteed yes. There will be at least one problem, either on the multiple choice or the free response, where you have to graph each side and find where they intersect. All right, rock stars, we're on to problem 3. So let's go ahead and talk about this bowl of soup. I did not have soup for dinner tonight. That's actually for tomorrow. So I'll make my wife do some fun math problems before she gets to eat soup, and that will end poorly for me. So let's get to it. Um, Part A asks you to use the data from the table to find this integral. We just did this problem on the previous page, so I think you can do that one on your own. We are going to talk about Part B, but then you guys are going to do Part C, and don't forget it's going to ask you to do a trapezoidal sum, so it'll be good practice for you to remember your area of a trapezoid. But I mentioned Part B, so let's chat about that. Use the data from the table to find the average rate of change of t of x over the time interval x equals 4 to x equals 7. Now, I find a lot of people get confused about average rate of change versus average value, and here is a great time to discuss it. So I'm going to give you two different formulas, and we're going to break down what each one means. You might not even want to write these yet, because I'm only going to use one of them. So, average rate of change, you might be tempted to say, oh, that's the 1 over 7 minus 4 times the integral from 4 to 7 of t of x dx. But then someone else might say, well, whoa, I thought we learned this average rate of change things was where we do t of 7 minus t of 4 divided by 7 minus 4. Which one is it? All right, well, there's actually a third one that we need to consider, but we'll go into that after we discuss these two. So, it's all about units. Average rate of change. So what is this asking us for? It's asking us for the rate of change of t. And the rate of change of t of x is t prime of x. It is the derivative, the rate of change of t of x. So whatever our formula is, it better give us units that are all about t prime. So average rate of change, well, let's think about what those units are. If t of x is in degrees Fahrenheit, then t prime of x is going to be degrees Fahrenheit per minute, and just for fun, t double prime of x will be degrees Fahrenheit per minute, or degrees Fahrenheit per minute squared. So t prime of x degrees Fahrenheit per minute means then that our answer to one or more of them, one of these, better be degrees Fahrenheit per minute. Let's begin with our red expression over here. How do we look at these units? Well, first we think about what do all these numbers mean? Well, 7 minus 4, 7 and 4 I think come from the table up here. Those are in terms of minutes. So I'm actually going to include some units down below. So we have 1 over minutes, 1 is unitless, times, the integral is just summing things up, so that's not going to have any units. But what about this t of x? Well, t of x from the table we know is degrees Fahrenheit. You can think of this as over 1 if you'd like. And then dx, well, that's the change in x values. And the x values here have units of minutes, over 1 if you will. So as we go through here and you multiply all these out, what's going to happen? Well, these minutes reduce and you end up with just degrees Fahrenheit. So this entire expression will tell us something about degrees Fahrenheit. What is happening here? Well, essentially you're doing the antiderivative of capital T, which is bigger capital T, but then you're dividing by minutes. And so you're going to undo the antiderivative and bring us back down to where we started. This formula is the average value of T of x. It is the average temperature over the time interval 4 to 7, not the average rate of change. This is out. What about this next one? Well, the numerator has degrees Fahrenheit because it's T of something, right? It's T values. And the denominator is in minutes. So our answer here is going to be in degrees Fahrenheit per minute. This is what we want. However, I promised you a third one. There is another way to get this answer, and the other way is to say, well, wait, this is the average rate of change of t prime. Couldn't we also do 1 divided by 7 minus 4 times the integral from 4 to 7 of t prime of x dx? Won't this tell us the average value of t prime? And because it's t prime, isn't that degrees Fahrenheit per minute? Yes. This formula here is exactly the same as the formula to the left. It's just written in a different way. This formula on the left is written if you have t of x. Here's a quick way to do it. If you don't have t of x, then here is a way to do it. They both do the same thing, but because we have values of t of x, we are going to use this middle guy. So now, excuse me while I erase all of this and then rewrite it so we can actually do some math here. Though I think the math becomes somewhat trivial, right? The point of this isn't an algebra class, it's a calculus class, and we just talked about the calculus part. Average rate of change. Okay. T of 7 minus T of 4 divided by 7 minus 4. And we jump up here. T of 7 is 99 minus 101. 99 minus 101 divided by 7 minus 4. I hope I can do this math. Negative 2 over 3. If a problem gives you units, it's always a good idea to include those units in your answer. Now, Part B did not ask us to include units, and so you wouldn't be dinged for not doing it, but you should do it. It's good practice, and it's easy. You just go straight across. You say, oh, the numerator, Fahrenheit units, denominator, minutes, and so we get negative 2/3 Fahrenheit per minute, which means on average, T of x is changing by negative 2/3 degrees Fahrenheit per minute. I kind of like the interpretation. It means that on average, as 3 minutes go by, your temperature reduces by 2 degrees. Right? If you wanted to write that as being over 1, a unit rate, if you will, we just cheat here and we write it like this. This says essentially every 1 minute the temperature is decreasing by 2/3 of a degree. And that's that. All right, let's scoot on to problem 4 here. Problem 4, I'm going to touch on every problem, at least A and B, but we're going to do part C together. So what's happening here, though? We're given the rate at which water is being pumped into a tank is given by the continuous increasing function r of t. And they give us r of t from 0 to 20. Now this is the first time we're seeing a problem that could be a potential AP question, because this table is giving us gallons per minute as our rate. That means that capital R of t is like a derivative. Remember, on the AP exam, you're usually going to be given an equation that's a derivative, a table that's a derivative, or a graph that's a derivative, right? Our first 3 did not give us derivatives. They gave us kind of the top of the ladder. So let's go through those units really quickly. R of t then is going to be in terms of gallons per minute. R prime of t will be in gallons per minute, and really big R of t would be in terms of gallons. How would I actually notate that? I would just pick a new variable, but I'm just being silly. So we are given this guy in the table, which is the derivative of really big capital of R. Now, part A, write Riemann sum for subintervals. You guys can do that. Is your approximation greater than or less than the true value? Now, this is something we haven't discussed yet this video, but we've done it before. Riemann approximations are all about the shape of the graph, and they told us about R of t. In particular, they told us that R of t is increasing, and it looks to me like all the values are positive from 25 to 46, so I just cheat and draw a random increasing positive graph, make a few subintervals, and we do write Riemann sum. So on my first subinterval, we go on the right side, and we draw that, right? We go on the right side and draw over, and same thing, and draw over. We can clearly see that all of these rectangles over approximate the area beneath the graph. So the reason for your answer is as R of t is increasing, then a right Riemann sum will approximate, or will over approximate the actual value. All right, let's move on to B. Part B, model for the rate as the water is being pumped into the tank is right there, and W of t is measured in gallons per minute again. That means it's a rate. That means we're dealing with a derivative. Use the model to find the average rate at which water is pumped in. This is a rate. We want to know the average of this function. So this is not, and I'm going to erase this, is not W of 20 minus W of 0 divided by 20 minus 0. This would give us the average W prime, and W prime in this case would be gallons per minute, right? They asked us the average rate at which water is pumped in the tank. We want our answer to have the same units as W of t. We want our answers to be in gallons per minute. So for this one, you're just going to have to set up that average value. 1 over 20 minus 0 times the integral from 0 to 20 of w of t, and I'm just writing out the function here, dt. And you're certainly not going to do that by hand. This is calculator practice. Put it all into your calculator, hit enter, get your answer. Don't forget the units will be in terms of gallons per minute. But the one we're going to focus on is part C. The tank contained 100 gallons of water. Use the model given in part B to find the amount of water in the tank at t equals 20. So we have an equation that tells us gallons per minute. We want an answer in gallons. How do we go from gallons per minute to gallons? Gallons per minute to gallons is an integral. So let's set this up. We are supposed to use the value at t equals 0, and I want to find the value at t equals 20. So we know we need to integrate from 0 to 20. Of what function? W of t dt. Right? Remember, W of t has units of gallons per minute, and a change in t has units of minutes. Multiplying those together gives us a final answer in gallons. How do we do this? Well, let's define a new variable that stands for gallons, and let's just use g. Let's say that gallons is going to be g. So I'm going to say that the antiderivative of capital W is capital G. And by the fundamental theorem, I know that's going to be g of 20 minus g of 0. Well, that's all exciting. But what am I trying to find here? I want to find the number of gallons after 20 minutes. We want to isolate that guy. So add g of 0 over to the other side, and that's going to give us that the gallons after 20 minutes are given by the gallons after 0 plus the integral from 0 to 20 of W of t dt, right? Manipulating that fundamental theorem. We've done that several times now. The tank contained 100 gallons. How do we find this part? Oh yeah, calculator time. And again, I said as soon as I know that this is a calculator active problem, especially on a free response, I put this equation into my calculator, and I'm not kidding. So when you look at my calculator, I literally type this in. I usually just type it into the graphing screen because I'm not always sure if we're going to have to graph it or do calculations with it, so it's safer to put it in the graphing screen. Hit enter. I see nothing, not a surprise, but I don't need that because all I'm going to use my calculator for is actually very similar to what you did up above. We're going to do all this on the calculator. Okay, so that integral then, we're going to go back to our other screen. We're going to go menu, calculus, integral, and we're going from 0 to 20 of what equation? Oh, it's in my graphed equation. It's in F1. Notice it turns bold, of x dx. 0 to 20. That looks pretty good. Awesome. 685.099. I want more decimals. 685.099. I guess I do not. And actually, that's probably worth discussing an answer in just a second. So 100 plus 685.099. I get that right? I did. Cool. Then I can even actually do this math in my head because we are superstars like that. This is going to be 785.099, and don't forget units, gallons. Just a heads up here, and this comes up every now and then. If you round this to 685 point and then you round all the way up to 0.1, that is acceptable, but you actually have to put the extra zeros at the end. They require you to do that so that you know you're not giving them an exact answer of 685.1. This is not 685.1. If you round it, there's 0.1, but there are more decimal values past that, and so you do have to show that there are more decimals by filling in these 0, 0. Just one of those random things that comes up every now and then. And that's honestly why I prefer not to round. Sometimes things can get a little tricky that way. But same idea though. If this was 0.090176 and you're like, oh, I'm just going to write the first 3 decimals, you do have to write the 0. Okay, it's not a 0 here, but you do have to write that to show them it goes forever. You have to go out to 3 decimal places, and 0 is a number in that case. Alrighty, let's jump on to problem 5. I'm actually not going to do any of problem 5 completely, but I will help you set up each one. Problems 5 and 6 are going to be talking about velocity. We need to remember that velocity is also a derivative. It's a rate. And they're actually going to be talking about 2 different cars here. So we have car A, and so they've denoted velocity as v sub a of t. Then later on, they're going to talk about car B, and they talk about the acceleration of car B, A sub B. So I wanted to go through and remind you of what these units will look like, and we'll just do this for car A, but car B is similar. So we have V sub A of t. Our units here are in feet per second. If we find the acceleration, which is the derivative of v, then the acceleration of car A will have units of feet per second, velocity, and we're seeing how velocity changes, so over time, feet per second per second. This, of course, is found by doing d dt. However, if I wanted to go from velocity to position, and I'm going to use x to represent position, we're moving on a straight road. I picture the x-axis. I think y would be kind of weird, right? Because then our car is going up and down, and then we have a very strange futuristic car. So we have x sub a of t, which will have units of feet. And to get there from velocity, we need to do the integral with respect to t. All right. Use the data in the table to approximate the acceleration of car A at 8 seconds. Indicate units of measure. Well, if this is velocity and they're asking us about acceleration, then we are using a derivative here, except we can't do the derivative at a specific point because we don't have an equation or a graph to measure the slope. Instead, we use our application of the mean value theorem, and so I would probably set this up like so. I would say that the acceleration of car A at 8 seconds is equal to the derivative of velocity of car A at 8 seconds. Those are exactly equal. I think it's very important to establish the relationship of what is given to what you're trying to find. Then we're going to approximate this by doing v of, not v prime, v of, we're going to use our table, v of, oh, and I think 8 is between 7 and 10, isn't it? Whoops. V of 10 minus v of 7 divided by 10 minus 7. And I'll leave you to do the rest of the work there. Units of measure, super easy. We already know our velocities up above. We know our times at the bottom. In fact, we know our final unit should be this guy. Part B, use the data to approximate the distance traveled by car A over this interval using a trapezoidal sum. So what are we trying to find? We're integrating here. We're looking for distance. This is just feet, not feet per second. We're going from 0 to 10 of v sub a of t dt, and that's going to be approximated by your trapezoidal sum. You can also see the units here. V sub a of t has units of feet per second, and dt has units of seconds, right? We end up with feet. Part C. Car B travels along the same road with acceleration of blah, blah, blah. At time t equals 3 seconds, the velocity of car B is 11 feet per second. Which car is traveling faster at t equals 7 seconds? So I think we're going to have to compare both cars here, right? So we're going to have to compare the speed of car A, and then we're going to have to compare that to the speed of car B. Now, speed is just part of velocity, but the car is going to be moving forwards the entire time, I assume, based on this. So all of these are positive, very exciting, and so all of these ones are going to be positive as well. So in this case, velocity will be the same as speed. We're moving to the right at that speed. And the speed of car A is very easy at 7 seconds. We just need the velocity of car A at 7 seconds, and oh hey look, we have a table. 61 feet per second. 61 feet per second. Cool. But the speed of car B is trickier because they gave us acceleration here. Rude. So I think instead, if we have acceleration and we want to know about velocity, we're starting here, we need to work back. I think we'll need to, I almost said integrate an integral into this problem. We're going to need to use integration. And in particular, I would use the fundamental theorem of calculus. You can do it with plus c, but I think it's a little more efficient this way, and it's good practice for you. We are going to find the integral. Okay, we know something about t equals 3, so I'm going to go from 3 to 7 of the acceleration, so that's 2t plus 2 dt. And I know when I do the antiderivative of acceleration of car B, that's going to give me the velocity of car B evaluated at 7, fundamental theorem, minus the velocity of car B evaluated at 3. This is our fundamental theorem of calculus. And since we're looking for t equals 7, I want to isolate that. So I know that the velocity of car B at 7 is going to be found by the velocity of car B at 3 plus the integral from 3 to 7 of 2t plus 2 dt. And now you just have some math to do. You can do this on your calculator or practice it by hand. It's not terrible. We are given this is 11 feet per second. And then don't forget a conclusion, right? After you find whatever this is, better compare it to 61 feet per second and tell which one's greater. So take some time, work through that, and I'm going to go ahead and move on to problem 6. 6, we're going to do somewhat the opposite of what we just did, and I'm actually going to work through all of this with you. So a particle moves along a horizontal line, so I'm going to call the distance x of t, with a positive velocity. V is a differentiable function, right? If V is differentiable, it also means V is continuous. And the time t is measured in seconds, velocity centimeters per second, velocity is given below. Based on the values in the table, what is the smallest number of times at which the velocity of the particle could equal 20 centimeters per second? Well, they gave us velocity. They're asking us about velocity. Let's just look at where 20 fits in. I have to go from 37 all the way over to 38 without skipping anything because V is continuous. So what happens here? Well, to go from 37 to 17, don't we need to cross over 20 somewhere in there? Not necessarily at 1. It could be at 0.1 or 0.2 or 1.9, but 20's got to be there. We go down to 1, then we start going back up again, have to get to 20 again over here. All right, well, how do we do this then? Or how do we state this conclusion? Well, first, the only reason that the particle has to cross over all these is that V has to be continuous. But it's never stated that V is continuous, so we do have to make that connection. So I'm going to start with that. As V is differentiable, then V is continuous. We're only going to have to state that once if we need it down below, which we might. We've already said it once, so we're good to go. Okay, what's next? As 20 is in between these two, right? So 20 is in between V of 2 and V of 0. So we're going to say V of 2 is less than 20, which is less than V of 0, right? That's just stating this right here. 20 is in between those outputs. And we'll do it one more time up above. Let's see. V of 10 is less than 20, which is less than V of 12. Then the IVT, this is the intermediate value theorem. 20 is in between or intermediate to 37 and 17. Guarantees at least 2 times where the velocity is 20 on 0 less than t less than 12 seconds. Yeah, the more we practice this, the more comfortable we're going to be with conclusions. Why are you allowed to use the IVT? What had to happen to use the IVT in the problem? And then a quick conclusion. Alright, based on the values in the table, what is the smallest number of times at which the acceleration could be 0? Well, now we have velocity. They're asking us about acceleration, which to me is a derivative. The only way we guarantee derivatives if you don't have an equation is through the MVT. And the MVT asks us to take derivatives. So what I'm going to do is if I'm looking to find 0, then I want to look up here and see, are there any guaranteed endpoints in the table where the MVT would give us an answer of 0. And looking here, I see these guys. In particular, I see that the V of t values are the same. And so I think when we find the slope, we will end up with 0. Now, you could certainly argue, you can make a very good argument, that there are many other values where the slope will be 0 as well, and you could probably get full credit, but I'm just going on based on the values in the table, so I'm just going to use what's given to me. So here we go. Mean value theorem. What do we need to show first? We need to show the slope of the secant line, the slope of these endpoints. So I'm going to find v of 10 minus v of 2 divided by 10 minus 2, our slope. And v of 10 was 17, v of 2 is 17, and this is 8, which is 0. Awesome. Because we're doing the slope of velocity, we are guaranteeing something about the derivative. Alright, so the smallest number of times at which the acceleration could equal 0, well, certainly one time. I don't see any of the same numbers up here, so I'm just going with 1 for now. Okay, alright, as v is differentiable on 0 less than t less than 12, and v is continuous on 0 less than or equal to t less than or equal to 12. How do we know that? Well, we already said as v is differentiable, then v is continuous. You have to explain that. Okay. And the, let's say, we could say the slope of the secant. Let's do the average rate of change. The average rate of change of v on, and I'm going to go from 2 to 10, right? I found the slope from 2 to 10 here. On 2 to 10 is 0. Then the MVT guarantees. Okay, what does it guarantee? It guarantees the acceleration, which we're going to say is v prime of t, must equal 0 at least one time on 0 to 12. Now you could say, well, shouldn't we do 2 to 10? Well, if this is a sub-interval of this guy, then it's assumed there. You could be more wordy if you would like. Alright, my guess is I probably made up this problem, which is why I think there are more answers to it, but that's essentially what they're asking. Alright, find the average acceleration of the particle over the time interval 8 to 10 seconds. Show the computations that lead to your answer and indicate units of measure. Average acceleration. So we want acceleration units. What are my units up here? Well, let's write that out quickly. We know that v of t is in centimeters per second. If we take the antiderivative, x of t will be in centimeters. And then I think a of t will be in centimeters per second per second. And we find that by taking the derivative of velocity. Okay, so let's get that done. So average acceleration is going to be found by taking the derivative of velocity. So I think we just have to do v of 10 minus v of 8 divided by 10 minus 8. Okay, v of 10 is 17 and v of 8 is 6. 10 minus 8, so we end up with 11 over 2, or 5.5. I'd say keep it as a fraction so you don't make a silly mistake like I did. How do we do the units? Well, the denominator is velocity, that's centimeters per second. The numerator is centimeters per second. The denominator is seconds. And I realize that seconds should be abbreviated with S so you don't confuse it with secant. For some reason I always just write SEC. I don't know. So either way, there's that. You could have also written this as, there's that 4.5 again, 5.5 centimeters per second, and that's fine too. Average acceleration. We've taught the derivative of velocity. Notice that this is also average acceleration up above. Last but not least, use a midpoint Riemann sum with 3 subintervals of equal lengths and values to approximate the integral from 0 to 12. Okay. I'm actually recording this right after my topic 5 exam, grading it, and I would say the most commonly missed question was on a midpoint Riemann sum. And I think it was because people tried too hard to understand what a midpoint Riemann sum was from a table. And so what I'm actually going to do is graph this. And I think as soon as I graph it, you're going to very easily identify the important intervals that you'll need. But what are we trying to do here? We're trying to integrate from 0 to 12 of v of t dt, and we're going to approximate this. Okay, graph-wise, I'm going to actually do it up above just because so I can see all the values here. You can do this on your paper, probably in the box at the bottom. I think you'll have enough room. So let's take a look. Okay, 2, 4, we have to all the way up to 12. So 2, 4, 6, 8, 10, 12. Good enough there. Put it 12 just so I don't forget. Okay, and this is in seconds. All right, the y values, the smallest one I see is 1, and then the next one I see is 5 and 6. The spacing doesn't matter. I would just make the spacing equal all the way through. Then I see 17. I have 3 more to go. 17, 37, and 38. And then let's look at each of these points here. In particular, though, I don't need all of the y values. So maybe before we look at the points, we should think about what a midpoint Riemann sum with 3 sub-intervals means. Well, the entire interval goes from 0 to 12. If I want to split that into thirds, that goes back to my delta x. The length of the interval is 12 minus 0, but I want 3 sub-intervals, which means each interval is going to be a length of 4. So first sub-interval, second sub-interval, third sub-interval. 3 rectangles, 3 sub-intervals. Then we want to do a midpoint Riemann sum, which means on my first subinterval in red, we want to use the midpoint of this interval to find the height. Where is the midpoint? Hopefully it is fairly obvious to you that it is at 2. So what is the height? Well, at 2, the height is 17. So I'm going to draw up and then fill out my first rectangle. Then for the next one, the midpoint between 4 and 8 is clearly 6. So we go from 6 just up to 1 this time. And then last but not least, well, look at this pattern. Here, I bet the last one's over here. But let's double check. Oh yeah, 10 is in the middle, and it's a value of 17. Once you have those, this gets really easy. Every subinterval here has a length of 4, so 4 times something, 4 times something, 4 times something, and then we have 3 heights, 17, 1, 17. So we have 4 times 17 plus 4 times 1 plus 4 times 17. Midpoint Riemann sum. If you're not sure how to do this without a graph, draw a graph. Could I have figured this out without a graph? Yes, because I've practiced this a lot, right? I would have said, okay, it's a length of 4, so here is 4, here is 4, and here is 4. Look at the midpoints. Midpoint, midpoint, right? So you can get it without the graph, but draw a graph if you get stuck. Okay, as we go through, you could factor out the 4, and you could add 17 and 17 is 34 plus 1 is 35, and that might make your multiplication easier. 20, this is going to be 140. What are my units? Well, V of t had units of centimeters per second, and time was in seconds, so that means my units are centimeters. What did this tell us? Well, I think this probably told us the total distance traveled here. However, we already did particle motion, so we have to think to ourselves, well, wait, was this the absolute value? But since everything is positive here, I think you could probably make the leap that this is the total distance traveled. So the particle travels 140 centimeters. So we want to give the answer in context, but also when. An integral tells about an interval. So the particle travels 140 centimeters from t equals 0 to t equals 12. Explain when that happened. Versus a derivative talks about what happens at a specific point. Hopefully you guys got a bunch out of this tabular data exploration. Don't forget that the rest of my solutions are posted on Teams, so there were many that we didn't go through and you'll need to finish those off. But I really do think you're going to be much more comfortable with finding approximating derivatives, Riemann sums, everything we've gone through and done. And that should be awesome and get you ready for our next lesson, which I'm excited to have you back for next class.